Welcome! In this session, we'll explore an interesting problem titled Race Car. Together, we'll break down the problem, analyze different approaches, and understand the most efficient way to solve it. Let's dive in. Imagine you are driving a car that starts at position 0 with a speed of 1 on an infinite number line. Your goal is to reach a specific target position as quickly as possible, in the minimum number of moves. The car can perform two types of actions. The first action is accelerate, which increases the car's position by its current speed and also doubles its speed. For example, if the car is at position 0 and its speed is 1, accelerating moves it to position 1 and increases its speed to 2. The second action is reverse, which changes the direction of the car. If the car is moving forward, it will reverse and start moving backward, and vice versa. When reversing, the speed is reset to 1 in magnitude, so it becomes either positive 1 if the car is moving forward or negative 1 if it's moving backward. Given these mechanics, the task is to determine the minimum number of instructions required for the car to reach a specific position, represented by the variable target. The output for this problem is a single integer, representing the minimum number of instructions needed to reach the target position. To understand this better, let's look at an example. Suppose the target is 3. Here's how we can reach it. First, we accelerate, which moves the car to position 1 with a speed of 2. Then, we accelerate again, which moves the car from position 1 to position 3, with a speed of 4. Notice that we've reached the target in just 2 instructions, both being accelerate. So, the output for this example is 2, and the sequence of instructions is represented as AA. Now consider another example where the target is 6. The car starts at position 0 with a speed of 1. First, we accelerate, moving to position 1 with a speed of 2. Next, we accelerate again, reaching position 3 with a speed of 4. A third acceleration moves the car to position 7 with a speed of 8, but now the car has overshot the target. To correct this, we reverse, which changes the direction of the car and resets its speed to -1. Finally, we accelerate, moving backward to position 6 with a speed of -2. This sequence requires 5 instructions, 3 accelerates, 1 reverse, and another accelerate. Therefore, the output is 5, and the instruction sequence is AAARA. Let's look at a slightly more complex example where the target is 10. Starting at position 0 with speed 1, we accelerate 3 times in a row. This moves the car to positions 1, 3, and then 7, with a final speed of 8. At this point, the car overshoots the target, so we reverse, resetting the speed to -1. Then we accelerate, moving the car backward to position 6 with a speed of -2. Reversing again changes the direction and resets the speed to 1. Finally, one more acceleration moves the car to position 10 with a speed of 2. This process takes a total of 7 instructions, 3 accelerates, 2 reverses, and 2 more accelerates. The instruction sequence is ARRA, and the output is 7. The problem comes with a few important constraints and edge cases to consider. The target position is always between 1 and 10,000, and the car always starts at position 0 with a speed of 1. The goal is to minimize the number of instructions needed to reach the target. For small target values, such as 1, the solution is straightforward, just 1 accelerate is enough. For much larger target values, like 10,000, the car will need a careful combination of accelerations and reversals to reach the target efficiently. There are interesting scenarios to handle, such as when the car overshoots the target and must reverse multiple times to adjust its position. Another notable case is when the target is an exact power of 2, like 2, 4, or 8. In such cases, the car can reach the target directly through successive accelerations without needing to reverse. These considerations make the problem both challenging and intriguing. To solve the race car problem, let's first consider the brute force approach. The intuition here is to simulate all possible sequences of instructions, using it to accelerate and to reverse, starting at position 0 with a speed of 1. By exploring all combinations of these commands, we can represent the problem as a tree of state transitions. A command moves the car in the current direction and doubles the speed, while our command reverses the direction and resets the speed to either +1 or -1, depending on the previous direction. However, this approach quickly becomes infeasible as the number of possible sequences grows exponentially with the depth of the tree. many states are revisited, leading to redundant computations. For large targets, such as 10,000, this results in impractical time complexity, making the brute force solution computationally expensive and inefficient. To address these issues, we turn to an optimized approach using breadth-first search, or BFS. Now, by treating the problem as a shortest path search on a state space graph, BFS allows us to explore all possible states layer by layer. Here, each state is defined by a tuple containing the car's position and speed. Transitions occur through two commands, a, which moves the car to a new position while doubling the speed, and r, which reverses the direction and resets the speed to either +1 or -1. Using a BFS algorithm ensures that we always find the shortest sequence of instructions to reach the target. A queue is used to manage states as they are explored, while a set keeps track of visited states to eliminate redundant computations. This not only ensures efficiency but also dramatically reduces the state space. With a time complexity of approximately O, target *log, target, BFS is computationally efficient and well suited for this problem. Additionally, pruning revisited states avoids unnecessary work, making the algorithm scalable and clear in implementation. These features highlight why BFS is an ideal choice for optimization problems like this. However, we must also consider some trade-offs, such as the additional memory required to store visited states in queue elements. While this could become a bottleneck for extremely large target values, it remains far more manageable compared to the exponential complexity of brute force. Other alternatives were also considered. Dynamic programming, for instance, is a promising approach that relies on breaking the problem into smaller subproblems. However, it requires careful formulation and may consume more memory than BFS, making it less practical. Another option is bidirectional search, which involves running BFS from both the starting position and the target simultaneously. While this could theoretically reduce computations, identifying an optimal meeting point between the two searches is challenging and complicates the implementation. Ultimately, the BFS approach strikes the best balance between simplicity, efficiency, and scalability. It avoids the complexity of DP and the challenges of bidirectional search, while still guaranteeing the shortest sequence of instructions. This makes BFS the most practical and effective strategy for solving the racecar problem. In this problem, we are tasked with simulating the movement of a car that starts at position 0 with an initial speed of 1. The car can execute two commands, a for accelerate, which doubles its speed and moves it forward by the current speed, and a for reverse, which resets the car's speed to -1, allowing it to change direction. The goal is to find the shortest sequence of these commands to reach a given target position t. To solve this, we use a breadth-first search, or BFS, strategy. BFS is ideal here because it explores all possible paths to the target in order of increasing number of steps, ensuring that we find the minimum sequence. We use a queue to manage the states of the car, where each state is defined by its position, speed, and the number of steps taken. Additionally, a visited set is used to track states we've already processed, which helps avoid unnecessary computations and ensures the algorithm remains efficient. We begin the BFS simulation by initializing the queue with the state 0, 1, 0, representing the starting position at 0, speed of 1, and 0 steps. As long as the queue is not empty, we process each state by dequeuing it and checking if the current position matches the target t. If it does, we immediately return the number of steps as the solution. For each dequeued state, we generate two possible next states. The first is the result of the a command, where the car moves forward based on its current speed and doubles its speed for the next step. The second is the result of the r command, where the position remains unchanged, but the speed is set to -1 if the car was moving forward, or 1 if it was moving backward. These new states are added to the queue only if they haven't been visited before, ensuring we avoid redundant calculations. After processing a state, we mark its position and speed as visited. To handle edge cases, we allow the car to reverse direction if it overshoots the target, enabling it to adjust its position. Additionally, we prune the search space by ignoring states where the car's position exceeds 2 times the target or becomes excessively negative, as these are unlikely to contribute to the optimal path. Similarly, speeds that grow too large are pruned, as they may lead to unnecessary exploration of irrelevant states. The BFS approach is particularly effective here because it guarantees that the first time we reach the target, it will be with the minimum number of steps. By using the visited set, we ensure that no state is processed more than once, which significantly reduces computational overhead. These optimizations, such as pruning and using the visited set, keep the algorithm efficient by focusing on the most promising states and ignoring those that are unlikely to be part of the optimal solution. To implement this algorithm, we use two key data structures. The first is a queue, which is essential for BFS traversal. It stores the states of the car, represented as tuples of position, speed, and steps. The operations on the queue include adding new states to the back and removing states from the front for processing. The second data structure is the visited set, which keeps track of all processed combinations of position and speed. This prevents redundant calculations by ensuring that we do not revisit the same state multiple times. In terms of complexity, the time complexity is proportional to O, t log t, in the worst case, as BFS explores all reachable states within valid bounds. The space complexity is also O, t log t, as both the queue and the visited set store the same number of states. Together, these data structures and optimizations ensure that the algorithm is both time and space efficient. The pseudocode implementation begins by initializing the queue with the starting state 0, 1, 0, and an empty visited set. While the queue is not empty, we process each state by dequeuing it and checking if the position equals the target t. If it does, we return the number of steps. For the command, we calculate the new position and speed, and if this state hasn't been visited and is within valid bounds, we add it to the queue and mark it as visited. For the R command, we adjust the speed to reverse direction and similarly add the state to the queue if it hasn't been visited. This ensures that all valid states are explored systematically. If the queue is exhausted and the target hasn't been reached, we return -1, though this scenario is unlikely given the problem guarantees that a solution exists. To illustrate how the algorithm works, let's consider an example where the target t is 3. We start at the initial state, 0, 1, 0. The first step is to accelerate, which moves the car to position 1 with a speed of 2, resulting in the state 1, 2, 1. Accelerating again moves the car to position 3 with a speed of 4, resulting in the state 3, 4, 2. At this point, the car has reached the target in just 2 steps, so the output is 2. This example shows how BFS efficiently identifies the shortest sequence of commands to reach the target, leveraging the systematic exploration of all possible states and ensuring that the solution is optimal. This solution employs a breadth-first search (BFS) approach to find the minimum sequence of commands required to reach the target position. The BFS strategy is well suited for this problem as it systematically explores all possible states, position and speed combinations, level by level. ###explanation. 1. Initialization ***. A queue is initialized with the starting state 0, 1, 0, representing the car's initial position 0, speed 1, and the number of steps taken so far 0. A visited set is used to track visited, position, speed, states and prevent redundant computations. 2. BFS loop ***. The BFS loop continues until the queue is empty. At each iteration, the current state, position, speed, steps, is dequeued. If the position matches the target, the function immediately returns the steps value, as this is the shortest sequence of commands. 3. Accelerate command ***. The car's position and speed are updated using the command, new_position equals position plus speed and new_speed equals speed *2. If the new state, new_position, new_speed, is valid and hasn't been visited, it is added to the queue and marked as visited. The position check ensures we don't explore states too far from the target, up to 2 * target for efficiency. 4. Reverse command **. The car's speed is reversed, reverse_speed equals -1 if the car is moving forward, speed 0, and 1 otherwise. The state, position, reverse_speed, is added to the queue and marked as visited if it hasn't been processed earlier. ###complexity. Time complexity ***. The BFS explores all valid states, and the number of states is constrained by the position and speed limits. The worst case complexity is approximately 2 to the power of n, where n is the number of bits in the target. Space complexity ***. The space complexity is proportional to the size of the visited set and the queue, which store the states. This algorithm ensures an optimal solution by leveraging BFS to explore the shortest path first, and the visited set prevents redundant calculations, ensuring efficiency. Here, we start by importing the necessary utilities and defining our solution class. The main method, racecar, takes the target position as input. We use a queue to perform breadth-first search, where each state in the queue is represented by an array containing the current position, the current speed, and the number of steps taken so far. Initially, the car is at position 0, with a speed of 1, and no steps taken, so we add this starting state to the queue. To avoid revisiting the same states, we use a hash set to store visited states, formatted as strings combining position and speed. Next, we enter a loop that continues as long as there are states in the queue. Inside the loop, we dequeue the first state to process it. If the current position matches the target, we return the number of steps taken to reach it. Otherwise, we simulate the first option, accelerating. This updates the car's position and doubles its speed. If this new state hasn't been visited and it stays within valid bounds, we mark it as visited and enqueue it for further processing. The second option is to reverse the car's direction. Here, the speed is set to -1 if the car is moving forward, or 1 if it's moving backward. This essentially allows the car to change direction without moving from its current position. We then check if this new state, represented by the current position and the reversed speed, has already been visited. If not, we mark it as visited and enqueue it with the step count increment by 1. This ensures that we explore all possible paths efficiently. If the queue is exhausted without finding a solution, which theoretically shouldn't happen given the problem constraints, we return -1 as a fallback. However, this situation is highly unlikely since the BFS guarantees the shortest path to the target will be found as long as the target is reachable. This completes the Java implementation of the racecar problem. To begin solving the problem where the target is 3, we initialize our queue with the starting state 0, 1, 0. This represents a position of 0, a speed of 1, and 0 steps taken so far. We also initialize a set to track visited states, starting with 0, 1. In the first step, we dequeue the state 0, 1, 0, and consider two possible actions. First, if we accelerate, the position becomes 1, the speed doubles to 2, and the total steps increase to 1. This results in the new state, 1, 2, 1, which we add to both the queue and the visited set. Alternatively, if we reverse, the speed becomes -1, leaving the position unchanged at 0 and increasing the steps to 1. This gives us the state 0, -1, 1, which is also added to the queue and visited set. At the end of this step, our queue contains the states 1, 2, 1, 0, -1, 1. In the next step, we dequeue the state 1, 2, 1, and again evaluate the two possible actions. Accelerating moves the position to 3, doubles the speed to 4, and increases the steps to 2, resulting in the state 3, 4, 2. This state is added to the queue and the visited set. Reversing, on the other hand, changes the speed to -1 while keeping the position at 1 and increasing the steps to 2, which gives the state 1, -1, 2. This state is also added to the queue and visited set. The queue now contains 0, -1, 1, 3, 4, 2, 1, -1, 2. Next, we dequeue the state 3, 4, 2. Since the position is 3, which matches our target, we terminate the process. The total number of steps required to reach the target is 2. Now we consider a new example where the target is 6. We start with the same initial setup, a queue containing the state 0, 1, 0, and a visited set initialized with 0, 1. First, we dequeue 0, 1, 0, and evaluate the actions. Accelerating results in the state 1, 2, 1, while reversing results in 0, -1, 1. Both are added to the queue and visited set, leaving the queue as 1, 2, 1, 0, -1, 1. Next, we dequeue 1, 2, 1. Accelerating moves the position to 3, doubles the speed to 4, and increases the steps to 2, producing the state 3, 4, 2. Reversing results in the state 1, -1, 2. These are added to the queue, which now contains 0, -1, 1, 3, 4, 2, 1, -1, 2. Finally, we dequeue 3, 4, 2. Accelerating moves the position to 7, doubles the speed to 8, and increases the steps to 3, giving the state 7, 8, 3. Reversing leads to the state 3, -1, 3. Both are added to the queue, resulting in 0, -1, 1, 1, -1, 2, 7, 8, 3, 3, -1, 3. The process continues as we systematically explore all possible moves to reach the target of 6. This involves reversing and adjusting speed at appropriate steps to optimize the total number of moves. Eventually, we reach the target position of 6 in 5 steps. Now, let's look at another example where the target is 4. Again, we initialize the queue with 0, 1, 0, and the visited set with 0, 1. First, we dequeue 0, 1, 0. Accelerating leads to the state 1, 2, 1, and reversing produces 0, -1, 1. These are added to the queue, which now contains 1, 2, 1, 0, -1, 1. Next, we dequeue 1, 2, 1. Accelerating results in the state 3, 4, 2, while reversing results in 1, -1, 2. These are added to the queue, leaving 0, -1, 1, 3, 4, 2, 1, -1, 2. Then, we dequeue 3, 4, 2. From the state 3, 4, 2, accelerating moves the position to 7, doubles the speed to 8, and increases the steps to 3, resulting in the state 7, 8, 3. Reversing changes the speed to -1, keeps the position at 3, and increases the steps to 3, producing the state 3, -1, 3. Both states are added to the queue, leaving 0, -1, 1, 1, -1, 2, 7, 8, 3, 3, -1, 3. By reversing and adjusting speed strategically, we eventually reach the target position of 4 in 5 steps. This approach relies on breadth-first search to explore all possible sequences of moves in a systematic way. The visited set ensures that redundant states are avoided, optimizing the process to find the minimum number of steps required to reach the target. To analyze the time complexity of this algorithm, let's start by understanding how the car's states are represented. A state is defined by the car's position and speed, where the position can vary between 0 and 2 times the target value. This range accounts for the possibility of overshooting the target. The speed, on the other hand, can double in magnitude with each step, both positively and negatively, making it range from -2 to the power of k to +2 to the power of k, where k represents the maximum number of steps. The total number of unique states is proportional to O, target times log, target. This is because the position has a linear dependency on the target, while the speed grows logarithmically as it is bounded by powers of 2. Using breadth-first search, the algorithm explores each state exactly once, thanks to the visited set that prevents revisiting states. Since each state involves constant time operations like calculating the next position or speed, the total time complexity is determined by the number of states explored, which is O, target times log, target. The overall time complexity of the algorithm, as discussed, is O, target times log, target. Now, let's examine the space complexity. The space usage primarily comes from the BFS queue and the visited set. The queue is responsible for storing the states, which include position, speed, and the number of steps taken so far. At most, the queue will hold all unique states, which is proportional to O, target times log, target. Similarly, the visited set, which ensures no state is revisited, will also store all unique position and speed combinations, making its space usage O, target times log, target, as well. In addition to these, the algorithm uses a constant amount of auxiliary space for variables like position, speed, and steps, which is negligible and considered O1. Therefore, the overall space complexity of the algorithm is O, target times log, target, aligning with the time complexity. Comparing this optimized BFS-based approach to a brute force solution helps highlight its efficiency. A naive brute force method would attempt to generate and test all possible sequences of commands to reach the target. Since the number of such sequences grows exponentially with the number of steps, the time complexity of brute force becomes O2 to the power of k, where k is the maximum number of steps required. This exponential growth makes the brute force solution impractical for larger target values. In contrast, the optimized BFS solution significantly reduces the computational cost by pruning unnecessary states using the visited set and restricting the search space. By limiting positions to the range between 0 and 2 times the target and speeds to powers of 2, the algorithm avoids redundant explorations. This optimization brings the complexity down to O, target times log, target, making it far more efficient and scalable for larger inputs. Analyzing the best, average, and worst-case scenarios provides further insight into the algorithm's performance. In the best case, the car reaches the target in the minimal number of steps without overshooting. While fewer states are explored in this scenario, the asymptotic complexity remains O, target times log, target. In average and worst-case scenarios, the car may overshoot the target multiple times, requiring a greater number of states to be explored. However, the BFS algorithm ensures that even in these cases, the exploration remains bounded and efficient, with the complexity still limited to O, target times log, target. This efficiency stems from the mathematical structure of the problem. The total number of states is the product of the possible positions and the possible speeds, yielding O, target, multiplied by O, log, target, which simplifies to O, target times log, target. Since BFS explores each state exactly once and avoids revisits through the visited set, the algorithm prevents the exponential growth seen in brute force approaches. This makes the BFS solution both time and space efficient for solving the racecar problem. When solving the racecar problem, there are a few common mistakes to watch out for. First, overlooking edge cases can lead to incorrect solutions. Examples might include the smallest possible inputs, very large target values, or situations where no commands are actually needed. Testing against these cases is crucial for ensuring the robustness of your solution. Another frequent issue is improperly tracking the car's speed and position, especially after executing in our command. Some implementations reset the speed incorrectly, which can throw off the entire simulation. Debugging step by step can help uncover such errors. Furthermore, inefficient state exploration can lead to performance issues, particularly for larger inputs. If your solution revisits the same position speed pair repeatedly, it may end up timing out. Using a visited set to track explored states is a great way to optimize this. Finally, overcomplicating the problem is a trap many beginners fall into. Instead of pre-computing all possible sequences or diving into convoluted logic, you should focus on clear, structured approaches like BFS or dynamic programming to keep the solution manageable. Now, let's discuss memory optimization and some key insights for interviews. Forgetting to manage space efficiently in DFS solutions can lead to stack overflow or excessive memory usage, especially with deep recursion stacks. Pruning unnecessary recursion or switching to an iterative approach can help mitigate this. In interviews, recognizing that this is essentially a shortest path problem on a state space is critical. Interviewers often want to see how quickly you can identify this and propose BFS or dynamic programming as a solution. Efficient state representation is another important aspect. How you encode position, speed, and commands can directly impact the performance of your solution. Keep it concise to avoid redundant calculations. Additionally, be prepared to discuss the trade-offs between BFS and DFS. BFS is generally preferred for shortest path problems due to its guaranteed optimality, but it does have higher memory requirements. Finally, you should be able to explain how your solution handles tricky edge cases, such as large target values or situations requiring minimal commands. The racecar problem also shares similarities with several other LeetCode problems that involve state space exploration and shortest paths. For example, LeetCode 127, word ladder, is another shortest path problem, but it focuses on word transformations rather than car movements. LeetCode 773, sliding puzzle, involves rearranging tiles to reach a target configuration, which also requires careful state management. Similarly, LeetCode 847, shortest path visiting all nodes, involves visiting every node in a graph while minimizing the path length. These problems all challenge you to design efficient search strategies and manage states effectively, making them great practice for improving your problem-solving skills in this area. There are several alternative approaches to solving the racecar problem, each with its own strengths and weaknesses. BFS, or breadth-first search, is the most common method since it's well-suited for shortest path problems. It systematically explores all possible sequences of commands while maintaining a queue of states. The main advantage is that it guarantees the shortest path, but it can be memory-intensive for large targets. Dynamic programming is another option, where you use a table to store the minimum number of commands needed for each state. This avoids redundant calculations and can be highly efficient, but it's often harder to implement and debug compared to BFS. Bidirectional BFS is a more advanced technique that starts from both the initial state and the target, meeting in the middle. While it converges faster, it's more complex to implement and requires careful memory management. Finally, there's the greedy simulation approach, which uses heuristics to make decisions. While it can be effective in some variations, it doesn't guarantee optimality and should be used cautiously when exact results are required. Great job! To recap, we explored the racecar problem using an efficient BFS and dynamic programming approach. Remember to practice similar problems to strengthen your algorithmic thinking. Thanks for joining, and don't forget to like, share, and subscribe for more content. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!